Okay, guys, I'm going to go ahead and run through 12A real quick. Let's go ahead and get started. This is non-renewable energy sources. We will talk about renewable ones later on in the unit. All right. So first off, these are the objectives of this module or this section of the guide here. We want to be able to describe the use of non-renewable energy sources in the United States, and we have a few of those, right? And there's some that you might not even be familiar with as different, like natural gas. A lot of people usually think that we're talking about oil, but that's something that you're going to want to differentiate. They explain why different forms of energy are best suited for certain purposes. Why don't we use oil for factories, for generating electricity? Why is it used in cars? Why don't we use coal in cars? Why don't we use natural gas in all of our vehicles, right? So these are things that we're going to explain in a little bit based on the availability and the quickness of energy. Understand the primary ways that electricity is generated in the United States. This one right here, you're going to want to draw a graph or a picture of a energy generator and know all the parts. Okay? All right, fossil fuel is derived from biological material that became fossilized millions of years ago, and different types of fossil fuels take different amounts of time, and they're differentiated by time, and also the organic material. So they're differentiated by both the organic materials that they originate from and the amount of time it took to fossilize. All right, non-renewable energy, if I can find my pointer here. Non-renewable energy is energy with finite supply, primarily the fossil fuels and nuclear fuels. So it's very important to understand that nuclear is also considered a finite supplied energy source. Okay, nuclear fuel is fuel derived from radioactive materials that give off energy. It's important to note here that all of our nuclear fuel currently is from fission, nuclear fission. Yeah, we cannot do nuclear fusion very well on Earth yet, not sustainably anyways. What I mean by sustainable is it's hard to sustain the nuclear fusion process. All right, so let's get a breakdown of worldwide patterns of energy use. Worldwide, so you're going to want to know this and compare this with the United States. So look over this. You want to know the different types of units of energy. All right, BTU, British thermal unit. This EJ, you're going to want to know this. This is EJ is exajoules. And in your book, it tells you what the breakdown of how many joules are in an exajoule, how many kilojoules are in an exajoule, and all that good stuff. All right. So this is the breakdown of the world consumption of oil, coal, and peat. Peat is just a really basic version of coal. It's the least compacted and decomposed. It has some organic material still in it, okay, but it burns pretty quickly, but doesn't give you as much energy. All right. Here's our world patterns of energy use. Again, this exajoules right here. So you notice here that China's way up here. And then you compare that to the per capita energy consumption, gigajoules. So we have one of the highest overall energy consumption in the world. And we have a relatively high, we are second place in per capita energy consumption. But I want you to look at your attention here in Canada. They don't use very much energy overall, but their per capita is very high. And can you think about why per capita consumption in Canada of energy would be very high? Well, what time of the year do you turn on your AC? Or what time of the year do you use a lot of electricity? In the hotter areas, right? In the south, we use high energy consumption in the summer because it's hot, right? And in the northern latitudes, if we go up north, we use a lot more in the winter, right? Because it's very cold. So we heat our houses. And in Canada, it's nothing but cold there, right? All right, commercial energy use is an energy source that is bought and sold, right? So our utilities and things like that, or maybe even oil. Right. Subsistence energy use sources, countries that don't have access to the same type of infrastructure or vehicles that would even necessitate using fossil fuels for transportation. Subsistence energy source is usually going to be things where you are collecting materials to burn energy to survive on your own. You're not worrying about buying or selling or commodifying energy. This could be animal dung, this could be wood. You're going to see this a lot more in lower developing countries. All right, so look at our worldwide pattern use of energy. You're going to want to know this because there are lots of questions on the AP test that give you graphs, and they're going to ask you, based on this data from 1950 to 2000, it could be said that. So you're going to want to know how to read graphs. And you notice here that oil is still among the highest, but it is downward trending, right? You can see that natural gas is definitely caught up since 1950. These are going to be like actual gases, okay? We're not talking about liquid fuels. Coal is going down worldwide. And you can see that our very pitiful here. We're not really using our renewables here, but you can see that they're kind of on the rise, and that's because of China and because this stuff is becoming a little bit more unsustainable, right? Worldwide patterns of energy use. Okay, so again, this is just another way to look at the material and the breakdown of how it is used, right? So a lot of it is used in industrial. I would definitely know that. The majority of our energy use is industrial. It's the opposite of water, or not the opposite, but you remember that water was primarily used for agriculture and then industry. Here, energy is used for industry. Yeah. So make sure you know those graphs. You want to know this little acronym, energy return on energy investment, is how much energy you put in to extracting the energy either from the ground or from the potential energy of like coal. What did you have to do to get that? And that usually is asking about, let's see if I can get my marker here. This is usually talking about transportation. This is talking about actually manufacturing. And the fuels and energy that was used to actually perform these tasks, okay? So you can, if you use this equation here, you can kind of evaluate if something is efficient or not. So you may be using an electric refrigerator, like, oh, this electric refrigerator doesn't use any fossil fuels, it's not burning wood or coal, so it's very efficient. Wrong, right? You have to really think about the factories, things like factories and generators and things like that. The transportation, so back up here again, the transportation it took to get those materials like coal to those factories, and then you can really evaluate how efficient the return of that energy is. So the larger the energy return on investment, the more efficient the fuel, and that makes sense. So usually when you divide, this is just like a percent efficiency in physics. So mechanical advantage and things like that. So if you divide the energy obtained by the fuel and you divide it by the energy you had to put in to get it, you obviously want something that's as close to 1 as possible, because 1 is about 100%, right? Yeah, higher than that would be amazing. You don't really get that. Okay. So let's see here. Inefficiency in energy extraction and use. Coal provides an example of inefficiencies in energy extraction and use. Energy is lost at each stage of the process from extraction, processing, and transport. So these are the things you're going to want to mention in your FRQ when you're talking about efficiency. When we get into energy calculations, even if you can't do the calculation, you can answer things like this, right? How to save electricity, how to save energy on our processes. You should know that coal is probably is by far our most abundant fossil fuel, but it is very, very low. It's kind of inefficient, right? I mean, it produces a lot of carbon dioxide and sulfates that go into the atmosphere through impurities. Our efficiency in transportation. So let's talk about this. Why is this important? We do not live in a very well grid network society. We don't have a lot of multi-use residential areas that have places where you can work within walking distance. And we're not a developing nation. We are a relatively industrialized nation. We're post-industrial. So it is just a foregone conclusion that we are going to need to transport ourselves. So now we can talk about the efficiency of the energy use in that transportation. And this is where you get into like high occupancy vehicles, hybrid vehicles, SUVs, right? All these things really matter when we're talking about efficiency and sustainability. And nearly 30% of energy used in the United States is for transportation. This is why efficiency in energy is important for transportation. Transportation is achieved primarily through the use of vehicles fueled by petroleum products like gasoline and diesel. Our buses will use liquefied natural gas sometimes, like propane. It's kind of neat. Okay, so look here. Look at the megajoules per passenger kilometer. Air travel. So if we went to work by airplane, it'd be really, really bad. But notice that it's way, way worse to just drive your car by yourself. And you can imagine the less gas efficient, the less fuel economy your car has, the higher this number is going to go, right? So what do you think would happen if you carpooled? What do you think would happen to this number if we went with 4 people? Well, if it was with 4 people, you would divide that number by 4. So it's already a lot better. Even if you just divided it by 2, you already are making it a better option than flying to work. How about that, right? Motorcycle is by far probably the most accessible, easiest way to lower the energy use per passenger, but it is, dangerous. Trains are really, really good. And the bus is really a pretty good option if we had better infrastructure of our cities, so we didn't have these gigantic spider webs that went all over the place. This might be better. So this would be something that we need to invest in, I think, right? So that way we can lower the energy transportation. All right, so here you can check this out. Cars, the energy kilometers per liter. So this is talking about fuel economy here. You can see that light trucks are kind of on the rise, cars are going up. It's worth noting that SUVs are still like the most popular vehicles to get, and that's really cool if you need them for work and all that, but a lot of the times people don't. They drive them by themselves. Our hybrid electric vehicles make up, I think, about 3% of all car sales, which is interesting, right? And there are some debates you can have about, the fuels you use to extract the lithium and the stuff for the batteries, the rechargeable batteries. Is it really worth it? It turns out that it ends up being a very carbon neutral buy when you factor in what had to go into making a hybrid electric vehicle, and then the fact that they cut most of their emissions out, or at least a good percentage of their emissions when you're on the road. So that's a good debate to have. But the consensus generally is that they are a carbon neutral thing. All right. So electricity accounts for 40% of our energy use. It can be generated from many different sources. A carrier is something that can move and deliver energy in a convenient, usable form to the end users. So we're obviously not burning coal in our houses, right? This is done offsite at a central location, and then wires or something carries the electricity over to us, right? Okay, so the process of electricity generation. Okay, thermal power plants. Thermal means what? That's heat, right? Heat. Okay? It converts potential energy in a fossil fuel, and we're talking about chemical potential energy, into electricity. When you burn things like coal, it'll break the bonds, the carbon bonds and other things inside the molecules, and those bonds are broken and they release their energy in the form of heat most of the time. That heat can be directed towards a turbine. We'll first boil some water. That steam will be vectored out of a pipe into like a turbine or like a little fan, which will spin, and it'll turn a generator, and it'll save or transmit electricity. An electrical grid is a network of interconnected transmission lines, so those power lines. It joins power plants together, and then from there we can link them and send that out to users. All right, so first off in that step is we burn coal usually. A lot of our factories are coal. We're starting to see a rise of a little bit of natural gas. Here's the steam. The kinetic energy of the steam goes to the blades. So we're having a transfer of energy. But it's worth noting here that when we are, when we're taking the potential energy out of the coal and turning it into kinetic energy, remember that we have the conservation of energy. No energy is lost or gained. So the total energy of that coal being burned is either converted into kinetic energy of the turbine, or it is converted to heat, right? And that heat is not going to be able to do work. So there's no work unless we come up with some crafty ways to use that heat, right? But most of the kinetic energy is going to perform work, right? And work is just a force times a distance, okay? So there are some ways, like through cogeneration, that we can use this heat to do some more additional work and raise the efficiency of our plants. That's pretty interesting, right? And the energy and steam turns the turbine, and the shaft in the center of the turbine turns the generator, right? Kind of cut off there. You're going to want to know this right here, know this stuff. So know this, and we're going to talk about ways to get rid of things like sulfur in the air through this exhaust pipe here. So we're going to pulverize the coal, make it really, really small, easy to burn. It's going to boil the water here. Look what's going to happen to the water. It's going to turn into steam. It's going to turn a turbine, which turns a generator, which goes into electricity. Transmission lines becomes part of the electrical grid. Now here the condenser gets cool water, puts in the boiler and also pumps hot water back out into like maybe a body of water. So like Calaveras and Bronick Lake in San Antonio, they do this. And if you swim near the output for the water, it's actually kind of warm there. It's kind of gross, but I don't know. It's fun. It probably affects wildlife. You probably are going to want to know about that. We have a range of survivability. We learned about that earlier in populations. Like it might be too hot for things to reproduce, but not too hot where they can't live, right? Okay, but it's worth knowing that a lot of our factories are burning here are going to be put back into the loop to turn the turbine. Okay. Efficiency of electricity generation, a combined cycle. This is some things you're going to want to know to increase efficiency. It uses both exhaust gases from steam turbines to generate electricity. So some of the those exhaust gases that were coming out of the chimney pipe will be vectored back in to spin that turbine. So it'll get more stuff out of it. Capacity, in reference to an electricity generating plant, it's the maximum electrical output. So it's how long you can keep the factory running for without having to turn it off and generating electricity. Now, it's even if you could make like 500 megawatt hours per day or something like that, it doesn't mean that you can turn it on for that long all the time. Sometimes you need to cool things down. They can overheat. Sometimes you need to repair things. Sometimes people need to go home. So are we automating our factories so that they can work even without people? All right, these are things that we need to invest in. This is part of our infrastructure, right? Okay, capacity factor, fraction of time a power plant operates in a year. So this is what we're talking about. So we're talking about capacity factor. You need to know that it's time, not the quantity of coal you can put in, but the time. All right, so cogeneration. This is pretty neat. The use of a fuel to generate electricity and produce heat. So this heat can be vectored back in to turn a turbine. Right. So there's heat lost. There's heat lost when you burn some coal. But if you can somehow make that heat spin something, then you get a little bit extra efficiency out of it, up to 90% sometimes. That's really, really nice. All right. In the next part, in 12B, we'll talk about our specific non-renewables such as coal, oil, natural gas, and then we'll also look at nuclear. And further on, we will talk about our renewable energy sources. Good job.